some of us have discussed yesterday that we might want to have a dinner tonight. And so there's otherwise no detailed plan yet. But one place that we will be using already in the end of the program in connection with the conference in the last week is a place in Skansen, or outside Skansen, near Skansen, which is which at least we have been to before, and you like. If you wouldn't mind going there twice, or those of you who stay for longer going there twice, that would be one possibility. Two other possibilities that come to mind right away are in walking distance nearby. One of them is an Indian place that's not too expensive. And by the way, in this case, this will not be covered by Nadia dinner. So there would be one Indian place which is not so expensive, and then there's a more normal or Swedish place, if you would like to call it like this, which is very good and is also nearby. And it's, I mean, what I meant by such a restaurant is that they have, for example, normally reindeer meat, for example, and then the typical price for such a meal, for the meat is for the meal is 250, I think. Could be, and that's high quality clearly. And
how about go to the Swedish place?
You would like to go there, and that's in walking distance, yeah. And that's a nice place. Right. I also like that very much. In which case, we should ask roughly, first of all, how many want to go, and then I can start. Then I can ask. I have no idea.
What is the place called?
Tasperhörnet. You know that?
Yeah.
Yes. So let me then write down. You'll find it on the internet, and I will send an email. I should make it right here.
It's kind of semi-improvised.
And then we have to decide on a time. So first of all, is that who of you would like this place, or who would like to join us if it's this place? So we have 1, 2, 3, 4, 5, 6. So roughly 7, 8 people. You're also coming. So then I gather this will be around 10 people easily. And should we? What time would you like?
8.
That's for Swedish standards really quite late, I think. I mean, the problem is perhaps that if you have that by 10 o'clock they might think, oh, you're still not ready. And of course we will not be ready by 10. So maybe 7 o'clock would be. I mean, I know that
7:30. Because 7 o'clock, I don't feel like eating either.
7:30. Okay, I can try that. Let me check this with Anne before.
You may get leftover reindeer.
What?
You may get leftover reindeer if you go late.
So who is? Let me ask. How do I ask such a thing? Who wants 7:30? And who would like 7?
No, Americans are
You would like earlier, right? Or
Okay, so let's go Swedish tradition.
what?
We're just trying to fit in with Swedish.
Yeah. No, I mean the last time already we had very well. We went. They asked us, "Are you still not ready or something?" Ah, that was with Lenny. Yes. Yeah. So some. I know you want to do something.
No, for me it was 8:30. So it's okay. Let's go with democracy.
Yeah, good.
So we have a menu here. It seemed to be that.
So can you explain about the menu while I just go to Anne? Andreas?
Yes. So it's very classical, very Swedish thing in the kind of in setting from 1709, I suppose, something. And it appeared that the prices for appetizers is around 150 and up, and entries is like 250-ish, I think. So it's quite expensive, but quite good. It's a place where you go for birthdays. So it's a good place, and I think it's very authentic Swedish stuff with herring and all that. Edge of it. Huh?
Edge up to 500, I guess.
No, it's not so expensive.
It was 300 for.
I used to go to much fancier restaurants.
So will we go from here then altogether, or
Matthew in
where is
English.
it?
We have to wait until the chief is able to reserve the table for us, and then we walk, yes.
Okay, so let's start the talk today. And so today's speaker is Jonathan Rougier, who is at University of Bristol in the math department. So he's basically a mathematician, statistician. However, Jonathan took his PhD and his basic degree and also PhD was in fact in economics. And then he moved into maths from that. And so presently, his present main field is uncertainty assessment for complex systems and applications mainly to climate and maybe also natural hazards and some other applications, but mainly climate applications. Okay. So please, the title of the talk is data assimilation, uncertain static parameters.
Thank you.
Or why is it difficult to calibrate dynamic models? That's right, please.
Thank you. So, good morning, everybody, and thank you for coming. This will be an old-fashioned talk. I hope that's okay for everyone. What I intend to do this morning is simply to reflect, I think, on some of the things that have emerged from the programme so far. I think that's more in the spirit of the programme, to see if we can take what we've heard so far and maybe make something of it, than presenting a piece of work that I have done prior to the programme. So I'm just going to give you an outline of some thoughts that I've had over the last 2 or 3 days reflecting on the issue of data assimilation. Right? Why data assimilation is much harder if you also have uncertain parameters in your model. And what the role in that case is of assessing the limitations of your model. And after I've explained the overline of the outline of what I mean by data assimilation with uncertain static parameters, I'm going to proceed in 3 stages. First of all, to look at perfect models with known static parameters, and then the news there is bad, right? And then perfect models with unknown static parameters, and the news there is worse. And then imperfect models with unknown static parameters, and the news there is not quite so bad. Okay, so this will be a 3-part talk after I've outlined the main things. And what I'm hoping to do is to give you an insight into the way that statisticians, like myself, come at the challenges of doing things like data assimilation. And the way that we proceed, of course, is not by thinking about actual numbers, but by thinking about procedures, right? And working out under what conditions certain procedures will generate good answers and or will generate bad answers. And I'll be talking about that today. So, I believe I'm to avoid black, is that right, Maxine? Was that?
Yeah, red is good.
So, is that big enough for everyone?
Yes.
Okay, so data assimilation. With uncertain parameters. So I'll just start by outlining what I mean by this in case it's not totally clear. So we have a deterministic dynamical model. So we have a model. And it says something like dx dt is some function of x, t, and some parameter theta. And that's what we mean by a static parameter. It's something inside the model. Think of it as a coefficient. on a differential equation. Now, if you have a very, very strong physical knowledge of the system that you're modelling, you may actually know the real equations almost. And in that case, it may be that the coefficients on your equations are actually operationally defined in the system. You can go out and make measurements, and then you can nail these things down. But mostly, when we're studying complex systems, we're not actually able to write down the equations that describe the evolution of those systems. Sometimes we can get part of the evolution. We understand what the ocean is doing. We understand what the atmosphere is doing. We don't really understand how they join together. Okay, so you have to incorporate into your model some physics which you don't really understand, and which therefore contains parameters that are uncertain. And of course, when you get to very, very complex systems, you don't even bother to try and write down the physics. I spent the last 4 years looking at glacial cycles. Right? So this is a model of glacial cycles. And there, we start from a phenomenological basis. So we don't even try to start with an ab initio model that describes the physics. We just say, what kind of connections do we expect to see amongst the observable properties of the system? So generally speaking, when you're looking at a complex system, this theta is unknown to you. And what you would like to do, of course, is you'd like to learn theta along with the trajectory of x. So if we were to take this, model and solve it forward, we could, for any given, time t naught, if I gave you an x naught, we could solve this trajectory forward in time. Okay. Maybe that's a glacial cycle. And then we can describe that trajectory with a function f, which will depend upon x naught and theta. Okay, so big F is the trajectory function, and it's indexed by time. And then clearly, in this situation, as I change x naught, or as I change theta, I will change the trajectory of x. Is everyone happy about that? So, yes?
Yes, sir. Is there a special meaning for the semicolon here?
For the
Semicolon we are using.
Only, not particularly in. With arguments, we tend to break them up into functionally equivalent types. So what we have here is an ordinate, t, which describes time, and then parameters, x naught and theta. So the semicolon is distinguishing between the ordinate and the parameters.
If you have two dynamical systems, as you, in your example, the ocean and the air, so wouldn't one use, for example, two differential coupled equations for that? And not a static parameter?
Yes, in fact, we use the term static parameter quite generally. Basically, the most general definition that I can think of is it's a parameter that may or may not evolve in time, but if it does, it has an evolution equation which does not depend upon the state equation.
You can, for example, take viscosity as a static parameter. Turbulent viscosity, say.
But in this presentation, I've tried to keep things as simple as possible. So think of this as just a coefficient in an equation.
It could be, like, for instance, suppose you have a really simple box model of the climate. Then climate sensitivity could be that.
It could be, exactly. It could be the weight on an egg in a box model, for example. In a hydrological model, that's exactly what it would be. Yeah, it would be a rate coefficient.
I'm surprised if you can have an evolutionary equation for theta. How can that be named static?
Well, so some of the things that are uncertain in complex systems are actually the forcing. And you might, for example, want to incorporate forcing as a quantity that's evolving outside the system that can be described by a parameter. But I mean, we could go into that in detail, but it's not important here. For us, everything for me is just going to be, without loss of generality, scalars, right? And so this will be an evolving quantity in time, and this will be just a number like 17.
But in capital F, the dot stands for t.
The index of time. That's right. So what we also have in the system, luckily for us, is we have a collection of measurements, and I prefer measurements to observations, made at well-identified times. So we have, for example, time t1, time t2, all the way up to time tn. And for each time we've taken a measurement, and that measurement is imprecise, so we'll represent the measurement as an error bar, so that's y1, y2, and I'm just going to assume that the y3, that the measurements are in the same space as the state vector for simplicity. And obviously with data assimilation, what we would like to do is we would like to match up the trajectory of the measurements. I mean, it's as simple as that. So the trajectory is basically a slalom sphere, right? and the measurements are gates, and to win the race, the star skier has to go through all the gates. That's exactly how it works. So, in the case of simple data assimilation, we treat the parameter theta as known, and we simply alter the value x naught. Okay? That would be data assimilation, or what we call, so let's record down here. Learning x naught, we would call that smoothing. Or learning trajectory xt, I think in general we would say that was smoothing. And then we would say that learning about theta, a statistician would call that calibration. So to calibrate your model is to try and learn its parameters. But actually, it also is useful to use another term for that, and that is the word tuning. And I find this a useful distinction. Calibration tends to be what statisticians do with a principled attempt to quantify uncertainty. If climate scientists will forgive me, tuning is what climate scientists do, where they just use a rather ad hoc procedure to try and make their model fit better. Okay, so if you want a distinction here, this is statistical and this is ad hoc. I mean, there are good reasons for why tuning climate models has to be ad hoc. It's just very, very difficult. But there's no attempt when you're tuning a climate model to quantify uncertainty.
You have to assume for smoothing that the model is perfect.
I'm going to go through 3 stages. So we're going to look at perfect models and then imperfect models later on.
Okay, but I mean, calibration would be more point in time, not from something that says that your model is imperfect.
Mm-hmm.
And smoothing would be, in your terminology, something that's assuming that your theta is perfect, you just a state.
Yes, so you're right in some sense, in that these are both marginal operations. But what we're going to do is we're going to do them jointly. So what we would like to do is learn simultaneously about both the trajectory of the state vector and the uncertain static parameters. So that is the combination of both of these things.
They're both part of data.
Well, I think data assimilation tends to focus mainly on filtering and smoothing. Right? I mean, data assimilation has arisen largely in meteorology. In meteorology, weather forecasting is definitely an initial value problem. Okay? So they've only looked at this. And that's because they don't need to worry too much about theta if you're doing a 5-day forecast for weather. But in climate, the initial conditions can be forgotten, basically. Maybe that's a mistake in practice, but it's what happens. And all of the uncertainty comes from 3 different things. There's not knowing the values of the parameters in your model. I mean, you have numbers for them, but you don't think they're the right numbers, and you would like to try some others. There's appreciating that the model itself is substantially in error, so that's accounting for the structural limitations of the model. And the third source of uncertainty in climate is not knowing the future. Okay? So those are the dominant sources of uncertainty in climate. And in climate, I think the focus switches much more to calibration, whereas in, maybe this is the operational distinction, whereas in meteorology and weather, the focus is on the state vector. So that's the outline of the problem. Now we're going to look at 3 cases of increasing difficulty. So, case 1, or A if you like, perfect model, known theta. Okay? So this is the perfect model data assimilation problem, where you know theta and all you have to do is try and recover the state vector. So what we need to do in this case is assert that there is a true value for x naught. So we'll call that x naught star. So x naught is in general an index to a function. So x naught star is a special value of x naught. Right? Is the true value. And that's going to be f t naught. I'll just write that x at t naught. And what we also need in order to make progress is we need a model for the measurements. So we need a measurement model. This is the system model, and this is going to assert that the observations yi are going to be, because this model is correct, they're going to be the trajectory at ti at the true value x naught star plus some error ei, where the ei's, following the standard treatment, are going to be independent normals with mean zero and variance 2r squared. This is a totally standard measurement error model. So the model is true, so we can simply insert the trajectory of the model into the measurement equation. There is a true but unknown value of the initial condition. So this is, if you like, the true process, right, under our assumptions. And here we have the problem corrupted by measurement error. And the measurement errors have precisions or uncertainties that we know about, which may be the same for all errors, but they may be different. So this is a perfectly specified problem, and we know how to deal with this problem after all having attended, or many of us having attended the workshop on data assimilation last week. If we were to do this in a variational method, we would create a cost function and minimize it. So the cost function that we would create would be j, and it's going to be defined on the index x naught, and it will be a function of the observed measurements. You'll notice here that this is the standard statistical convention. When things are random, they tend to be represented with capitals, so the measurement error is random, and therefore the measurement is random. And when things are specified, they tend to be represented with lowercase. So these yi1 to n, these are the actual observations. So this is a random vector, this is one realization of that random vector. Okay, these are the observations, and to stress that, I could write obs up here. I could do that everywhere, but it's just a bit tedious, so we'll just write it out. Just for this time. And then this is going to be our standard loss function, which is going to be take the observation, subtract what the model says, square the result, and divide by the variance. And variational data assimilation then is to start with this loss function, so I could have written an obs up there, and then simply to zoom around the state vector space, or the initial vector space, until you minimize this function, and then call the result your estimate. Okay, so x hat 0 is going to be the argument that minimizes over x naught in some space j of x naught and y and friend.
So there's a common H operator, which is the observational operator.
I assume in this case that we're making an observation directly on the state vector purely for simplicity. Okay? There's no loss of generality doing that. Yeah? So H is, so it's an identity operator. Okay?
Are you also assuming that there is no error in the initial condition?
So the initial condition is an unknown. In our perfect model, it's well defined. It just happens to be concealed from us. So in this perfect model scenario, if we knew the initial condition and we take it as given that we know theta, we can reconstruct the entire trajectory. So our data assimilation problem is simplified in this case to finding out what the initial condition was. It's not like there's an error in it, but it's certainly unknown to us at the moment, but we're hoping to recover information about it from y1 to yn. So this of course is just this is the variational approach. I believe, doing some talking to some friends and doing some more recent reading, that this would be known as 4D var with a strong constraint. Okay, 4D because it assimilates information through time. Strong constraint indicating that we're treating the model as perfect. So later on we're going to talk about 4D var with a weak constraint, which is where you allow the model to be imperfect. Okay, now this is interesting from a statistical point of view, and the reason this is interesting is because if a statistician was to look at this loss function, this cost function, and to contrast it with this measurement error process, you would see immediately that the solution to this problem is a maximum likelihood estimator. Okay, that follows immediately. So, from a statistical point of view, we actually know that the log likelihood at x naught is times half j. Now, the reason I mention that is because maximum likelihood is by far and away the most studied and most used of all point estimation techniques in statistics. So the only point I'm making here, of course, is this is totally respectable from a statistical point of view. There's no magic here. This is exactly what a statistician would do. It's not like the meteorologists have invented something new. They're doing something totally sensible and understood. What they're doing is they're doing maximum likelihood. Whereas we would normally maximize the likelihood, what they've done is they've minimized the negative of likelihood. Now, if you're a meteorologist, you perform this calculation and you end up with a number. Okay? Statisticians want to know more. They want to know what are the properties of estimators that have this general feature. And the key thing that a statistician does, which is probably different from what happens in meteorology, is they think about the behavior of this maximization process or minimization process under replications. So this is how a statistician thinks. If I knew what a typical statistician would look like, I would draw one at this point and then show him or her thinking. But actually, what I'm going to do is I'm going to say the value that we have, x hat naught, which is implicitly a function of the observations, okay, is one realization. Let's do this again. Of the random variable x hat naught of big Y 1 to n. So it's like nature dealt us out one particular set of realizations for the measurement areas. That allowed us to create one particular set of measurements, and we plugged those measurements into our procedure, and we generated one number, 7. The statistician asks, what is the property of this entire process? Rather than not what is the number, but what is the distribution of this number under the variability that we proposed in the measurement area. So the meteorologist does the data assimilation and derives a number like 17. The statistician asks, what is the nature of the distribution from which that number was derived? That is, if you repeated this process millions and millions of times with different realizations for the measurement error, what would this distribution look like? Does everyone understand that? Yeah, the distinction between the meteorologist generating a number and the mathematician asking about the properties of the process.
I think the meteorologists are also asking the same question when they are taking the ensemble approach.
Yes, exactly right. Okay. That's a very good point. In fact, I could say a lot more about this one, but I'm not going to. But you're right. I mean, the reason that we do this, of course, is because we want to understand the properties of this estimator. Because an estimator like this can have good and bad features. A good feature of an estimator like this is that it's correct on average. And you'd want, over many different replications of the measurement error, for you to get the right number on average. Another good property of an estimator is it has small uncertainty. Okay? But the general feature of these things is, this is called the sampling distribution of the estimator. And it is parameterized by x naught star. So, what can we say in general about sampling distributions, sampling properties of estimators? So, we've got a maximum likelihood estimator here. Do we have any general results about maximum likelihood estimators? Well, the fact is that for finite n, we do not. Right? There's so much flexibility in statistical modelling that you can't make any definitive statements for finite n, except in very, very special cases. But we do have some infinite n results, okay? So-called asymptotic results. And it turns out that one of the reasons that people like maximum likelihood, apart from the fact that you can do it, is that it has very powerful asymptotic behavior under quite general situations. And in particular, under quite general situations, you can prove that the maximum likelihood estimator cannot be beaten by any other estimator. Right? It is what's called efficient. Right? Another thing that you can prove, which I'm going to focus on today, is under quite general conditions, the maximum likelihood estimator is consistent. Now, to understand what I mean by consistent, you need to imagine that we can in fact increase the number of measurements, right, without limit. Now imagine that we could do that. We ask the question, if we were able to do that, what would be the behavior of this quantity here as n became infinitely large? Would it in fact collapse onto the true value x naught star, or would it not? Okay. Obviously that's a minimal desirable property of an estimator, because you would imagine that if you couldn't even nail x naught star with an infinite amount of measurements, then what on earth is the point of trying with 100? Yeah? So consistency is considered to be a minimal desirable property of estimators. Right? Formally we say that consistency, if x naught hat y 1 to n converges in probability to the true value x naught star. That is to say, with an infinitely large collection of measurements, this procedure would guarantee to return you the correct value x naught star. You have to say that you'd really want that, wouldn't you? Okay, that's pretty minimal. And in fact, under very general conditions, maximum likelihood estimators are consistent. But obviously, from the fact that I'm not going to stop here, the news is not so good. And in fact, basically, the problem that we face is that x hat naught is not consistent. And that's what I want to explore.
P means here limit of infinite number of errors.
P is convergence in probability. What that means effectively is that this has a distribution. As n gets bigger and bigger and bigger, this distribution will start getting more and more concentrated. And in the limit, it will concentrate to a point, basically a spike. And if you converge in probability, that spike will be at the true value x naught star. Okay, so if you had 100 observations, the sampling distribution would be quite large. If you had 1,000, it would be more narrow.
So this P is just a shorthand for all of that.
Yeah, convergence in probability. It's one of those funny things about probability that if you're thinking about limits in a standard mathematical setting, there's only one way for xn to limit to x. Right? And if you think about convergence in a probabilistic way, there are 5 ways, 5 different ways for xn to converge in a limit to x. Okay? And convergence in probability is the second weakest.
It's a bit like having a floppy rope and trying to make a certain shape in the rope just by wagging the end of it, really. And is that a reasonable analogy?
It could be.
Yeah.
I'm not quite sure.
Okay.
Yeah.
Is it something like that the probability distribution of x naught goes to a delta function in the limit of n going to infinity?
That's exactly right. So that's the technical way of putting it. We go to a Dirac delta function at x naught star. So if you imagine for n equal to 100, the sampling distribution might be quite wide, and for n equal to 1,000, it might be more spiked, and for n equal to 1,000,000, it might be really spiked. Then at infinity, we're expecting it to be a delta function at x naught star.
But it still doesn't say how fast the convergence is.
No, absolutely not. This is a result about convergence. It doesn't say anything about speed. We can actually get speed results with slightly more work. But you know, if you haven't got consistency, then the rate at which it's not converging is not really important. The fact is it's going to the wrong place.
But that should be, I mean, it really should, it seems like a very weak thing to say that just the number of observations goes to infinity. Maybe all the observations, you know, there are infinitely many, but still there are, you know, finite period of these that you don't observe at all.
Actually, that's that's a very important point. I'm going to come back to that. The way in which n goes to infinity does turn out to be important. But important for trying to recover from this blow. Right? We cannot fix this, actually. This is generically true, as I'm about to show you. We can show quite clearly that this estimator is not consistent. So there is no guarantee that even with an infinite amount of measurement, we could get the true value x naught star. And consequently, one is left floundering, wondering what happens in a case where, in fact, n is only equal to 100.
question.
Mhm.
X, you are not considering the accuracy of X in this development, so I guess if you were able to know exactly, accurately, to the infinite precision, then you will, it should work, no?
So,
There is a kind of uncertainty here.
are you talking about the measurement uncertainties?
No, the x0, because you're playing with x0 only to change the initial value, no? That's only what's left in this model.
That's right. That's my control variable.
Your control variable. So I guess that you should have a certain. This is the sensitivity to initial conditions that you're considering here.
Yes, in fact, it will come down to that. It's basically a shadowing property that I'm going to develop. Let's first of all understand why it is the fact that x naught hat is not consistent. And this does not require some heavy duty stat theory. Thank goodness. What can we write out here? Perhaps I can go this on this piece of board. Can everyone see this part of the board? So, we look at the most general proof of consistency, that is the one with the weakest conditions. Okay? The weakest condition requires 1 over n j x naught y 1 to n converges in probability to some limit. Okay? And in fact, that convergence has to be uniformly in x naught. That's not important. If you can prove that this quantity here converges in probability to a well-defined limit, then you're basically home. Okay? And unfortunately for us, the reason that we cannot prove consistency is because this quantity does not converge in the limit to a well-defined quantity. Okay? But this is convergence probabilistically because these y's are random. So what we're saying is the distribution of this thing does not collapse to a point, even as n becomes infinite. And the reason is that in order for this convergence to hold, we need the weak law of large numbers. Which is a very general result. This states that if, let's take one of these terms here, if each of these terms has the same mean, and each of these terms has the same variance, convergence is guaranteed. Okay, that's the weak law of large numbers. Very useful. So let's let ui be defined as this thing here. It's which is yi minus f of ti x naught over tau I all squared. Okay. So if e of ui equals e of ui prime for all I and I prime, and same for the variance. And that implies convergence, and that implies consistency. So in fact, our problem is, basically, that each of these terms has a different mean and a different variance. And that's why we can't get convergence. So if we look at the mean and variance of these terms here, assuming this picture is now agreed.
Does that mean that your f is as something like a distribution that has so extended wings that you cannot define a mean, or it could be Gaussians and they all have mean?
So these are Gaussians. The problem is, as I'll show in a moment, these i's, their means and variances depend upon I and x naught and x naught star, okay, which is an x, basically. And that's because of the recursive nature of the dynamical system. That's all it comes down to. It's about the presence of theta at every point in the time domain. So it's easy to show that E of ui, well, this I suppose is the critical step. So ui is its right hand capital Y in sign, so it's random. yi minus f of ti x naught over tau I squared. Now let's go in here and simply subtract and then add f ti at x star naught. Okay? So if you subtract ft I at x time naught, you get yi minus ft I x time naught, which is equal to ei. So it's going to be equal to ei. And then we're going to need to add on the difference where this is the crucial quantity, delta I of x naught is equal to, by definition, f at ti x naught star minus f at ti x naught. Okay? Now, ei is a Gaussian with mean 0 and variance tau I squared. And this quantity here, therefore, is recognizable to a statistician as what's called a non-central chi-squared. Right, as a well-known distribution. And it follows immediately that E of ui is equal to 1 plus lambda I, and the variance of ui is equal to rho 2, 1 plus 2 lambda I. Lambda I is delta I x naught over tau I squared. This is known as the coefficient of non-centrality. And all the point I'm making, of course, is simply that there's an I in here, right? Each of these terms in this sum has a different mean, a different variance potentially, and consequently, we cannot use the weak law of large numbers to establish the convergence of this sum, as then becomes infinite. And therefore we can't prove consistency. So consistency follows from the fact that there's an I in this expression. Yep. And there's an I in this expression. Or rather, inconsistency follows from that.
If the initial distribution is Gaussian with zero mean, you would change the result. If you assume that your initial distribution of uncertainty, the initial state is Gaussian with zero mean.
No, it would change nothing. If you wanted to introduce extra regularity information, you could just put another term on here,
Yes.
but it wouldn't change anything. All the conclusions that we're making here about the behavior of the likelihood function can then follow directly into the Bayesian case as well.
What is it saying? There's no line there.
The variance of ui?
Yeah, and what is that? What, I can't see that what you wrote. Is it 2?
Yes, 2, 1 plus 2 lambda I. So that's the problem, basically. The problem is simply the presence of these i's on the right-hand side. Okay? There were no i's, we're done. Okay? No i's mean that all the terms in this sum had the same mean and had the same variance. The weak law of large numbers then proves the convergence of this expression here. The convergence of this expression here is basically all that we need to get to consistency. Okay? So we do not have consistency because of the presence of these i's. And as I said to Sasha, that intuitively the reason that we're going to have consistency is because theta has a different impact at every point in the trajectory of x. Yeah, that's basically the feature of non-linear dynamical systems. That's what's going wrong.
So if you had the same measurement error in every measurement, then you
Wouldn't change anything. This would then become tau, but there's still an I in here, which is that the I is no.
But if you also have a linear system and initially the Gaussian distribution is zero mean,
Yes.
does it have
You're completely fine there, because you're describing a situation where ultimately the likelihood function is log quadratic.
okay.
So this is definitely about the general case where we're not going to rule out pathologies like non-linearity.
Yes.
Okay, so this is, yes.
Sorry, just a continuation of the previous question. So how does it get simplified in the linear case?
So in the linear case, this becomes a difference which is invariant to I. Right? And this term here, tau I, is actually going to effectively cancel because we could imagine standardizing all of these EIs by their variances and making these all identical. So in the linear case, we can actually lose the I from this big delta expression. But I'm not so interested in the linear case. I'm thinking about the non-linear case as being the one that's generating the interest.
So you're saying delta I is constant in the linear case?
I'm only speculating. I haven't thought about it hard, to be honest.
So the problem is that, of course, the function is non-linear. A given measurement error translates into very different consequences depending on your
That's
law
right.
of the relativity.
It comes back to this issue that theta does not play the same role at every measurement point. Yeah? Yeah? And that's the whole property of nonlinear systems. As you change the parameter of the system, some parts of the trajectory wiggle a lot, and some parts hardly wiggle at all.
That brings us back to the road.
Yeah, okay, that's the road. Okay, thank you, that's the road. Now, it's not all bad news though. So I think we can establish that in fact we have no consistency result for the data assimilation problem, and that is of course with a perfect model and with known theta. But there's some good news. So let me just explain why this is not as bad as it looks. Because I think this is the most interesting bit, actually. Because you're going to be saying to yourselves, if Olivia was here, he would definitely have said by now, he would have said, "Boff, I've been doing data assimilation for 30 years, right? It's a tremendous success, right? It cannot be the case that x naught hat is inconsistent, right? Otherwise, it would definitely have caused a problem by now. And the fact is, he's right. But it's interesting to try and understand why he's right. So this is a general result that says inconsistent. Now let's consider nearly consistent. An entirely new concept which I just made up. Nearly consistent.
So from a mathematical point of view, isn't it usually seen as either it is or not, and it's important not to do the grayscale?
Totally. I'm definitely a grayscale guy, so I've maybe crossed over into the physics camp a little bit here. So you can see the problem. The problem is that there's an I on the right-hand side. Right? Under what conditions would it not matter? Okay. Well, the variance condition dominates the expectation condition. So if we can make the I not matter in the variance, then it follows that the I won't matter in the expectation either. So let's have a look here. In order for all the variances to be approximately the same, we require that 1 plus 2 lambda I is basically the same as 1 plus 2 lambda I prime. Okay, that will do it. Okay, and that will then imply that 1 plus lambda I is roughly the same as 1 plus lambda I prime. So we can make the means and variances almost the same as each other if this condition holds. That would be good. Okay? So this condition holds if and only if 1 plus 2 lambda I is much, much less than 1. That would do it. I'm sorry, 2 lambda I is much, much less than 1.
Question. Is there an equivalence between, you have, I mean, you've not really proven that it's not consistent. You've just shown that you can't use the weak law of large numbers to prove it's consistent. But there's no equivalence between variances and means being equal, then it's convergent.
That's right. So what we can't do is we can't prove the weakest consistency theorem. That's not to say that the result is surely inconsistent, but we have no way of demonstrating its consistency.
You really need to use this law to be able to prove some...
Yes, the weak law is astoundingly weak actually. It doesn't even require that the quantities are independent of each other, only uncorrelated. It's really a very weak law. So I wouldn't rule out some ingenious calculation to come up with a slightly different set of conditions. But in order to make progress, the easiest thing we can do is, if we were able to recover this weak law result, then we would get back to consistency, and that would be a good thing. So we need, if 2 lambda I was much less than 1, then all these variances would be roughly the same, and then all the means would be roughly the same, and then we'd be back in the weak law world. So this is the case if and only if, and this is where it gets really interesting, because I'm going to take this lambda I, which is this quantity here, and I'm just going to rearrange things a little bit. So that's going to be f at ti x naught star minus f at ti x naught. It's got to be much, much less than tau I over root 2. Okay? And that's got to be true for I equals 1 to n. So that basically is the condition for weak consistency, which is a concept that we just entirely made up. Yeah? But to come back to Lorenz's point, what we're trying to do is we're trying to recover to get back on the road for the most general proof of consistency. And if we can make the expectations and the variances the same as each other, we're basically there.
I'm not it may be that we are actually going the wrong way. Because you can always satisfy these by having a very large error.
True.
And that would basically mean that if you have a very large error, you can basically fit anything to it.
You can. But remember, as statisticians, we're interested in quantifying uncertainty.
Yes, but then the whole thing becomes useless. Right?
Totally, yes. I mean, if you have an estimate for x naught hat, which is consistent, or which has an error of plus or minus 1,000, right, it is genuinely useless. The challenge here is to use a realistic appraisal of the measurement uncertainties and turn that into a consistent estimator of x naught star with an appropriate quantification of uncertainty. I'm not going to quantify uncertainty today, but yeah, I mean, you can always achieve a result by making a bogus assertion for your uncertainties. But what we would like to do is make a principled assertion for uncertainties, not simply dial up the measurement uncertainty until the problem is solved. I mean, that would just be a mistake. Yeah. These generally represent the properties of our instruments. We want to get a solution that is consistent with the physics, not a solution that just exists because we fiddled with the numbers.
Sorry, Jonty, is the tor I the space between the measurements? Is it?
That's it's a measurement uncertainty standard deviation.
Right. Okay.
But it kind of goes against the intuition that if you measure things much more accurately, you're actually worse off.
So it comes back to Lorenz's point. In that case, you can't prove consistency.
Yes.
Yeah. Let's talk about that now, because I think this is important. I want to understand the operational significance of this constraint. Okay? What does it mean in practice when we minimize the cost function? So let's draw a picture to understand what's going on. So this probably is the crucial picture. Let's look back at our trajectory in this time. A bit higher up. So let's assume that we know the true value. This is speculating that we know the true value of x naught star. And then we would solve the system forward, remember the model is perfect, and we would get a trajectory like this. Now we have measurement errors too, right? And they have widths. So let's put those widths onto this curve. T1, certainly have 3, T2, T3. And let's draw these error bars as plus or minus, say, tau over 4. So I'm putting them centrally on the groups. Yeah, that was quite tight. Now, what this construction is saying is that there are some x naughts which are very close to x naught star, for which all n of these conditions follow. Okay? So let's take an x naught that's really, really close. It's just a fraction away. So let's start at this point here, which is only just a tiny bit above x naught star. And let's solve the trajectory forward and see what happens. Okay? Stays really close. Maybe it crosses over slightly, but yeah. You can see that this trajectory lies inside all of the error bars. Okay? So that x naught satisfies this condition. Right? The absolute difference between the true trajectory and the x naught trajectory is much, much less than tau I over root 2.
In some sense, sensitive dependence on initial condition implies that for large enough t, there is never such an x naught.
Exactly the point I was going to make a little bit later, but thank you. That's exactly right. So implicitly here, we have to think about the length of the measurement period. But when we talk about asymptotics in a moment, that will be an absolutely crucial feature. Now let's look at a slightly smaller x naught, maybe this one here. And again, perhaps it's the case that it hits all of the targets. There we go.
X naught here, is that our best estimate?
X naught star is the truth.
Yeah.
X naught is an index. It's the number that we're varying to make smaller or larger in order to minimize the cost function.
Yeah, I understand this is the true value, X naught
That's the
star.
true.
What is X naught?
It's an index that we can try. It's our control variable. Yeah, it's the variable of candidate
So it's
values
not
for
a
X
number,
bar.
doesn't have a definite value, it's...
No, it's the index of the cost function. Remember, the cost function is j of x naught, 1 to n. And as you move x naught around, you move the trajectory, and therefore you change the cost function. And our objective is to find that value of x naught, which minimizes the cost function. We call that value x naught hat. And our hope is that x naught hat is very close to x naught star. In other words, that value that minimizes the cost function is very close to the true value. If we were to continue this experiment further, say we were a little bit further out here, say we try this one. It might be that it hits a couple of targets, but then maybe it misses. So this value up here does not satisfy this condition. Now you can imagine that if we repeated this experiment lots of times, we could enumerate a set of values, which I'm going to call curly n star, right, which is the set of x naught values in which you'll certainly find x naught star, right, for which this condition holds. Okay? If you go too far away here, you're going to miss at least one of the targets. Also, of course, if your measurement period is very long, ultimately you're going to miss the last target, right, no matter how small the perturbation. But within a fixed measurement window, there will be a collection of x naughts close to x naught star, right, which actually are going to hit all of these targets. Okay? They are going to satisfy all n of these conditions, and therefore they are going to satisfy our property of weak consistency, okay, weakly consistent. Now I'm going to turn this picture on its side now, so imagine taking this picture and rotating it around like that, and we're going to look explicitly at the cost function. So So we know that these cost...
In some sense, the number of members of n star goes exponentially smaller as t increases.
My view entirely. Let me take this point actually to clarify what we mean by asymptotics. In temporal and spatial statistics, there are two different asymptotic regimes. There's what's called fixed domain regimes, and there's what's called increasing domain regimes. Now, the fixed domain asymptotic regime is where you take the same measurement period and you imagine collecting more and more measurements inside that period. Fixed domain, okay? The density of measurements goes up. There's increasing domain, which is where, as you add more measurements, you tend to do it by putting them onto the end of the current set of measurements. So as your measurements goes up, the measurement period goes longer, right? And the density of measurements stays about the same. Now, I'm about to make the point, but I'll make it now anyhow, that under a increasing domain asymptotic regime, I fully expect n star to shrink to 0. Right? Because when you get all the way out here, even the slightest perturbation will cause you to miss this target. Yeah? So we have to think here about the asymptotic regime, which we would call fixed domain. But my view is that in the fixed domain regime, were you to add more points, right, most of them will probably satisfy this inequality that you already have, because if you've hit these targets already, then hitting a target in here is also quite likely. So we have to rule out increasing domain asymptotics because they're clearly not going to satisfy the condition that n star is well defined. Right? But I think with fixed domain asymptotics, it's quite possible that we could increase the number of n's and not substantially shrink the size of n star. So this function looks like this, and anyone who's tried to minimize these functions knows they look horrible. Okay. Now, what happens though is that they will become well behaved in the region where x naught is in the nearly consistent set curly n star. Okay, so what we'll have here is we'll have x naught star, the true value, and then we'll have curly n star, right, the set of values. This is typically what a minimization procedure looks like in this cost function. When you're well away from the nearly consistent region is all sorts of rubbish, basically. You have to jump over all these local minima. And then, when you get into the nearly consistent region, what you'll find is that one hopes for quite small numbers of measurements, you will get a fairly quadratic cost function, which will have a well-defined, one hopes, minimum. And the property of consistency is actually the property that, as n becomes infinite, this part of the function, right, becomes perfectly quadratic with a perfectly and uniquely defined minimum. And that, with consistency, that minimum will lie directly over x naught star. So this is what the space curly n star actually looks like in the minimization problem. Now, if you crank n up using fixed domain asymptotics, then what you hope to find is that for a much bigger n, say it's n equal 100, for a much bigger n, you want to have, yeah, that's fixed domain. You see, so the width of n star isn't going to change very much, but the behavior of the function inside n is going to become much smoother, and the minimum is going to become much more closely related to x naught star. So, with pure consistency, that's exactly what would happen. With full consistency, we'd end up with a cost function that did something up here and then straight down, touched x naught star, and went straight back up again. That is a well-defined minimization problem that will give you a perfect answer with no uncertainty. Of course, that would be in the limit as n became infinite for fixed domain asymptotics. Now, this is the picture as it looks, and the only thing that I have to say at this point is, of course, to remind you that we do not know where n star is. Okay? This is the catch. N star is defined around x naught star, and this is the uncertain quantity that we're trying to nail down. So, it seems to me that if data assimilation is a successful technique, and I fully believe that it is, then it must be because n star is big enough, right, so that any minimization routine will ultimately enter it. Right? Because once it's entered n star, the job is done. Once you're in n star, right, as long as you've got a fairly large number of measurements, then you're going to go straight down this quadratic curve, and you're going to hit the bottom, and you're not going to be too far from x naught star. Okay? But you don't know where n star is, so you've got to hit it in your minimization routine. And therefore, n star has got to be big enough for you to hit. If you start from a reasonable starting point for x naught, and you follow a minimization routine, you've got to get in here, because once you're in here, you're done. So I think that if there's successful data assimilation, it's down to the fact that n star is quite a large region. And that, of course, implies that on the kind of time scales for which we're running meteorological models, 6 hours, right, the trajectory is fairly invariant to small perturbations of the initial conditions. I think that's probably true for 6 hours, and certainly, and if Olivia was here, I think he would say that that was true. But of course, if you go out to 5 or 10 days, you're completely sunk. Like 5 or 10 days, the size of this has shrunk to nothing. You'll never hit it, basically. But for 6 hours, I think the reason that data assimilation probably works is because this unknown set is easy to hit in the optimization routine.
I can say, I know from practice that if you have very accurate observations and uncertain background state, you're not able to converge. And actually we increase artificially the errors in the observations to be able to get to some meaning.
We do, and it's not really cheating cost, because we do this all the time, but I'm going to make a point. I just need 5 minutes just to finish, if that's okay. Is that okay? I want to make 2 more points. This is basically all the analysis. It's not very complicated, but I want to make 2 more points in cases B and C. B is unknown static parameter, and C is imperfect model, and they both apply. They both can be thought of in this framework. So I think the news is good and bad. I don't think we have any reason to believe that x naught hat is consistent. I think we have to say that probably it isn't until further notice. But I think we do have reason to believe that in many systems we will have a large curly n star, that is a large region of nearly consistent outcomes, and our optimization routine will probably find its way into curly n star, and then we're done. So case B, uncertain theta. Now we only need one picture for this problem. It's this picture again, but now it's drawn in 2 dimensions. We have x naught as before along here. We have theta up here, and the set, curly n, will be a set in x naught theta space. Is everyone happy like that? It's a set of values of x naught and theta, which when you perturb them from the true value, leave the trajectories within the targets specified by the true trajectory and the measurement uncertainties. So this picture looks like this. Just think there. X naught there. Now what's this set curly n going to look like? Well, I'll draw what I think it looks like, and then we can discuss whether that's realistic or not. Let's put the true value x naught star theta star in. Okay. Now obviously the set curly n star contains this point here, because if you don't perturb away from it, then you sit on this trajectory by definition. Now I think it looks something like this. I think it has a lot of width in x. But not very much width in theta. This width in x, for the given theta, so that's the true value of theta, this width in x just corresponds to this width here. So if data assimilation is working, then probably n star at theta star is quite wide. So then we have lots of width at theta star. Right? Do you see why I've drawn this with almost no width in theta star? Right? Okay, so for any given value of x naught, the set is very narrow. Why do I think the set is very narrow? Well, really the same thing. It comes back to the fact that with nonlinear dynamical systems, structural instability is a key feature. That says that as you perturb the parameters, even a small amount, you can move the trajectory a lot. Okay? That is structural uncertainty in nonlinear dynamical systems. And it's pretty much taken for granted that that's true. Even in systems where perturbations of initial conditions don't move the trajectory that much, we can find that even small changes in the parameters can cause qualitatively different changes in the trajectory.
That's not always true.
Oh no, I mean, it's not always true, but
you
it's...
can have, for example, Hamiltonian dynamics in K and torides. Even when the nonlinearity is quite strong, the torides are mostly there.
And it's also...
So
it's always true in fluid flow as well. In fluid flow, it seems to be the case that you can perturb the parameters.
That depends on the kind of questions you are asking.
Yeah, it's true that...
what you want to measure.
I completely concur, and I think there will be situations in which this is large. And the kind of problems that I look at, where we use quite pathological nonlinear dynamical systems, typically systems that are periodic, right, chaotic, non-autonomous, and forced, and tend to resonate with quasi-periodic forcing. Right? You can make tiny changes in the parameters, and you can move the trajectory quite a lot. Right? Okay? In writing about environmental modelling generally, McWilliams, who was writing in particular about fluids, said that the characteristic of structural instability was a characteristic that had been found in every interesting model of these systems that have been studied. Okay, he wrote that in 2008. I have the quote here, actually. He said,
What was that?
McWilliams, yeah.
I think that statement needs careful.
He said structural instability is the norm for a broad class of chaotic dynamical systems that can be associated.
I think that needs a whole lot of footnotes.
I'm happy to take his word for it though at this stage. It's not important for what I'm saying, it's just my reason for thinking that in many systems, maybe not all of them, but in many systems, the width as you perturb theta will be very small. Right? Even a small change in theta will cause a large change in trajectory, and consequently, you will almost immediately, if you move theta, you'll miss the target. And if you miss the target, you're not in curly n star. Okay? So that's my reason for thinking that in many situations, this will be a difficult to find set in the joint space of the control parameters. Because now remember, you're optimizing jointly over x naught and theta. So your optimizer has to start from some point in the space and wobble around, and it's got to hit this set. You don't know where the set is, and then once it's hit the set, you're probably okay, then it's large. Okay, but you've got to hit the set. And if this set is almost a lower dimensional space than this whole space, your chances of hitting this set are very small indeed. Okay, especially with large problems where you have a vector of initial conditions and a vector of parameters. So it seems to me that there's a qualitative difference here, and I completely concur. I'm trying to make as general a statement as possible without looking at special cases, but I completely concur with the idea that this isn't a completely general statement that holds for all dynamical systems. But for many of the dynamical systems that we look at, which are non-linear, possibly chaotic, possibly non-autonomous, and often forced, right? That is, they have all the pathologies that you would like to see in dynamical systems if you're studying them for a challenge, then it's very often the case that small perturbations in parameters cause large perturbations in the trajectories, and therefore this is a very slim set, okay, and hard to spot. So that's why I think there's a fundamental difference between simple data assimilation, which is this problem, where possibly curly n star is quite large, and data assimilation with uncertain static parameters, which is this problem, where I think this set can be very hard to hit. It's to occupy a very small volume of the total control space. And then I have one more point to make. I'm actually not going to make it except in words, which is simply to come back to your point, which is that if you now allow your model, right, to be imperfect, and you quantify your imperfection with a standard deviation in the usual way, then what you find is that the condition that you must satisfy is more relaxed. It's more relaxed because what you end up with is f at ti x naught star theta star minus f at ti control parameter values x naught and theta must be quite a lot less than tau I at 4 plus 6. Where sigma squared is basically the standard deviation of the model's inadequacy. So if your model is accurate for plus or minus 5, right, at any point in time, your sigma is basically 2.5. Okay? So you can see that if you were to treat your model as perfect, right, then your sigma will be 0. This would be the same condition as before. Okay? Now as you allow your model to become imperfect, sigma becomes bigger than 0, and this number rises. This upper bound rises. And consequently, the set curly n becomes larger. Right? It becomes easier for you to hit the sweet spot in your control space, at which point, right, your minimization procedure will take you close to the true value x naught star theta star. Okay? So that's a very simple point, which I think is easy to demonstrate by allowing your model to be imperfect. If you allow your model to be imperfect, you get the flexibility, right, to hit the sweet spot. And we all know, right, that cranking up the uncertainty regularizes this curve. We all know it's true, and we all do it. Okay? Now, one thing you can do is you simply take your measurements, and you can make them more uncertain. Right? You can say, I know this is plus or minus 2, I'll call it plus or minus 4. Right? What you're doing is you're increasing this. Right? But another thing to do is to say, my model's not perfect, let me account for that by quantifying its imperfections directly. So keep the measurement error the same, but think about quantifying the model as an additional source of uncertainty. So you know, my model is never going to be more than, say, plus or minus 2 accurate. And in that case, again, what you're doing effectively is you're increasing the size of the sweet spot, and you're improving the behavior of your estimates.
That means that you must explicitly then introduce uncertainty in the model parameter.
Yes. In this case, we have uncertainty in both model parameter and
include optimization of some model parameter in the assimilation process.
Totally. I think that's really crucial. You see, when we write down models that are phenomenological, the parameters have no real meaning. They have an instrumental role, which is to generate the right dynamics. But they don't mean anything. It's not like you can do a measurement. And so they have to be thought of as part of the structure of the model that gets learned about by the observations. Okay? But the key thing that people are doing at the moment, of course, is they are saying, I can't get my optimizer to work, I'll just boot up the variances. Right? You can understand that by saying what they're really doing is they're trying to make the curve n star bigger. But actually, you don't need to boot up the variances. What you can do instead, within a framework that is well understood, is you can quantify your model uncertainty explicitly, and it has the same effect. It has the effect of making this unknown set a larger part of the control space and increasing your chance of hitting it in your translation.
It's not clear to me the difference between your perfect model uncertain theta and an imperfect model. By an imperfect model, do you mean I change the model by adding additional terms to the equation? I mean, are you making a distinction between parameters that can be changed and the functional nature of the model that can be changed? Is that the difference between these two?
Let me just explain what I mean by perfect model in this situation. That's a very good question because there's a quick and dirty way to do this, and there's a principled way to do this. And of course, I like the principled way, but this is the quick and dirty way. So the quick and dirty way is to assert the existence of x naught star and theta star, which are instrumental, right, such that your observation yi is f ti x naught star theta star plus some additional stochastic process to account for the limitations of the model, plus measurement error. So these two things together, right, are the model which is wrong and a first order, if you like, adjustment for the quality of the model, which is a stochastic process. Okay? That's the quick and dirty way of fixing this. You keep your deterministic model and you add on, this is called a discrepancy.
And then sigma is the variance of this
Yes.
noise.
In this case, what I've done is I've assumed the discrepancy is Brown in motion and stationary, and I've given it a variance of sigma squared, just for simplicity. But of course, you can generalize.
Are you assuming that the structure form of F is actually correct? Or would this be
No,
F prime?
Basically, this is a horrible fix. Basically, the idea is that F is incorrect, but
So
there
it
exists.
actually would be F prime. I mean, the way you're writing it down. makes
Well,
a little
so
bit-
yeah, this is no longer the process. This is just some abstraction.
it's some functional form.
Yeah, we're still solving the dynamical model, but we're not asserting the dynamical model is the system. We're asserting that the dynamical model is like the system in the sense that we can quantify the difference between the dynamical model and the system by the addition of a stochastic process. Now, this is it's horrible, right? I'm not trying to give any excuses for this. The correct thing to do is clearly, in my mind, to go entirely into stochastic modeling. Right? For me, if we have the DT in there, this is the right way to model, to statistically model limitations. You say that on the time step from t to t plus dt, right, the model takes you to here, right, but the system went somewhere slightly different. That's the purpose of the diffusion, is to account for the fact that on the time step the model is wrong. Okay? And I only mention this because, in fact, 4D bar with a weak constraint is actually using this framework to quantify the limitations of the model, which is really fascinating. Okay, so it's horrible and quick and dirty, but it gives us a very simple resolution in terms of result here. This is how you would do it in practice, which is what 4D bar with a weak constraint is actually doing. I think I probably better stop there, actually, so thank you very much. I'm sorry I went over.
Regarding this, the last two issues, you hypothesized an additive stochastic process. Could it be, and how would you distinguish? Could it be a multiplicative one through theta, for example?
Yes, this is just the most practical formulation of model limitations. In general, in this formulation, we assert that this process and the measurement errors are uncorrelated. And the simplest assertion also is that this process here has nothing to do with x naught and theta. Generally speaking, you wouldn't want to make that assertion. Right? You'd want to parameterize the distribution of this process with x naught and theta. So the additivity is not really the issue here. The issue is that if you want to use this framework, you have to work out what the impact of different choices of x naught are on this discrepancy term, because you can guarantee that it's not going to be neutral. I should give you a formal appraisal of this framework. Okay, this is the current standard approach in the statistical field of computer experiments, which is one of the areas where I work. Okay? People have been doing it this way since about 1997. That is, they've been including explicitly an allowance for the model limitations as well as for the measurement. Okay? Since the middle of the 1990s. It's a horrible framework, right? Except for the fact that outside the field of computer experiments, no one is thinking about quantifying model uncertainty at all. So outside of computer experiments, they haven't got this term. Now, frankly, if you were to contrast the two, it's much better to have a bad representation of model limitations than none at all. So if I look at my own field, right, I'm a bit embarrassed by what they're doing, but when I look outside it, to what's happening in the whole of the rest of science, right, I say it could be a lot worse. Right? So we've got 3 levels here. This is what I want to do, right, and this is actually implicitly what's happening in 4D bar with the read constraint. Right? This is what my field in statistics are doing, right, and they're struggling to quantify this term exactly. And this is what is happening in the rest of environmental science. People are running models with no explicit allowance for their limitations, except possibly by simply cranking up the measurement errors.
From a practical point of view, I would guess that the most natural thing is to take this model uncertainty. I mean, the model contains lots of parameters. Numbers in cloud parameterizations, RC exchange, whatever, lots of them. And to say that they're no longer fixed numbers, but some kind of variables. That seems to be more complicated than even the second thing that we're doing here.
You're absolutely right. So I've described the maximum likelihood approach to calibration. That's the front end of a Bayesian approach, where you treat the parameter themselves as uncertain, and you describe the prior uncertainty about them with a probability distribution. That would be my preference too. But this is simply a statement about the likelihood function, and this will follow straight through with the Bayesian analysis. In the Bayesian analysis, where you treat the parameters as uncertain and give them distributions, it's still the case that the shape of the posterior distribution will be strongly conditioned by what happens in the likelihood function. So what you're talking about is the natural generalization, which I would do too, but which would inherit all the features that I described here.
This is a comment, and this may be, of course, completely wrong. I think the way you are formulating the problem, you're probably shooting yourself in the foot. In measurements, one of the things you are dropping completely is the matrix which maps the observation to the state vector.
Yep.
That is actually never the case, never the practical case. I may be completely wrong, correct me if I am wrong, but reproducing the whole trajectory completely is probably a task which is never going to be successful. What probably we are looking for is to match statistical quantities. Even when observations are being performed, they are really not a point observation. They are really property of the system averaged over a small length and time. So then, if it is formulated that way, then probably there will be much more freedom in N star.
I agree. In fact, that follows exactly, it's a point that Andreas raised as well at the start. If you were to imagine there was an operator that took you forward from the state to the measurement, right? Rather than having the very simple case that I have here, where the measurement is on the state directly. So either a transformation, like an aggregate, for example, a spatial or a temporal averaging, or maybe some nonlinear mapping that involves a satellite or something like that. In that situation, the condition for near consistency is a condition that exists in the measurement space, as you might infer from the structure, and not in the state space.
Exactly.
Yeah, that's exactly right.
That's exactly the point.
Because all that happens is that you put the measurement operator here and the measurement operator here. And in fact, you're absolutely right, that makes your life a lot easier because the measurement space is lower dimensional and it's more highly averaged.
Yes,
yeah, so that's exactly right. So yes, in a way I didn't do my case justice because perhaps one of the explanations for N star being large in data assimilation is exactly that step.
In tabless modeling, perhaps sigma or epsilon is not Markovian, or maybe depends on X state. Can this formulation be generalized to
yes,
these two cases?
This is
non-Markovian dependent on X.
Yeah, this is the most simplest expression. Okay? In general, the distributional choices here and here, for example, are only made for trackability. They are implicitly the choices that must be made if the cost function in the variational minimization is a maximum likelihood estimator. So there are the choices that you must make in order to make current practice respectable. Yeah. But in a general theory of maximum likelihood estimation, you simply describe these objects probabilistically. There's no particular requirement for them to be Gaussian or these to be additive. And likewise, this becomes just if you like, a generic trajectory generating function. It doesn't need to satisfy a differential equation. And in fact, often they satisfy stochastic difference equations. In biology, for example, systems biology, this would be a stochastic difference equation that describes, for example, the evolution of of processes on a metabolic map, where the time steps themselves become random. So, and that's actually what a lot of statisticians are working on. They're working on these more complex cases. But just to understand what's going on, I've taken the paradigm in data assimilation, which seems to be consistent with the simplest possible case. Gosh, that was a long session. Didn't you call it today?
Okay, yeah. Thank you. We have, I have an announcement about the dinner. We would indeed go to, we have a table for 10, 1930. Actually, it was closer to officer. And so 1930, and we have to make a decision.
Democracy did not win, what happened?
We have to make a decision about the menu, what we all want to order. That was the condition.
Because we want to pre-prepare things?
I don't know.
That's strange.
It may happen that, say, if almost all of you order reindeer steaks, they will not have so much reindeer meat. So if they're told beforehand, if they're told beforehand, they will be ready.
And then,
it may particularly be bad for vegetarians.
Yes, indeed.
If there are any Swedish
I definitely want to eat reindeer, so you can cut me
on
the carnivorous side.
No,
I'm not a vegetarian.
I also see.
No, I never met an Indian that was not vegetarian. So
No, I'm not.
you're not?
And in fact, it turned out they don't have reindeer.
What? Where are we going there?
The reason is, during the season, it's May. I mean, we should come to this, of course, by September, October.
What?
No, not what? No, then it's reindeer, of course. Now nobody's now.
You are not allowed to kill the reindeers any time of the year.
No, that I understand, but I thought there were some, there are always wild reindeer.
No,
Yes,
there are
but you are not allowed to hunt them.
Reindeers.
The wild reindeers are a thing.
Oh, that's a pity.
Anyway, that's what we have. If you wanted to start this, then right. So let me start with the main course here. Cod, trout, steak, lamb, ox, risotto with oxtail, and beef fillet, diced beef fillet.
And still we have to take only one of them?
Maybe one of them. No. Everybody wants to order, and they want to make a table then, I think.
We have to.
Yes.
We have to choose now. Then we can take different
Sure,
meals.
yeah.
Okay, that's it. Much better. I thought we had to eat all the same things.
No. Is that okay?
Yes.
Yeah. Okay. Good.
So the main course. So why don't we start with the starter instead?
I think you also have the always on the corner.
Always on the corner. Casserole of
I
fish
think
and
that's
shellfish.
also included.
You want to start with the starter instead?
Actually, there is no vegetarian thing here.
That is correct,
Oops.
I think. I could ask, of course, specifically about that. How many vegetarians do we have? One?
No, you
Two.
fish.
I fish also.
Okay. You don't eat fish. Then I will ask for that. Okay, good. So we want. So then first of all, we begin to write down one.
You should do that on your computer directly in the file. At least you send the file.
No, then this way you see it. That's good. You know.
You see it since you are projected.
So you are not having dinner then?
No.
Okay. And how about you? Okay. Okay, we have one non-fish. That's me, yeah? That's. And that is, I don't know. So that's I think how we'll do it. Are you, Niels, having?
No, I'm not coming.
Okay. Jonty, are you having dinner? No. You're having dinner? And Franz, yeah. What's your first name actually?
Christian.
Christian, yes. Sorry. And yes, next one. What to make a choice? Dinner? Sasha.
I would like to comment. I haven't studied before.
What?
I would like to.
Yeah. Very good, very good. And I should write on your yes, something good. Okay. But the first surname was something with PGO, yeah? PGO, yeah? So,
Yeah.
any choices? Maybe what I should do is I put a number here. Oops.
There,
Oh,
close to the computer.
and by the way, yes. So I will make a number here. I'm sorry, that's so complicated. And let me then after. Right, so the reason, so we have starters and we have starters at very high prices. Okay, that's up to you. So. And we have anybody else having dinner? You're having dinner, right?
I have to do the talk tomorrow. I guess I will be busy this evening.
Okay. Are you having dinner? Yes. Anybody else? Everybody, right? And myself. And my son, I think. In which case we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then we need to complete. What it is, so this is what we don't have. So, what is your choice?
I think I'd take something, I think that was Simon on the always on the corner. If you would put it down. Last day cured Simon. The second from always on the corner.
Okay, so that is the second. That's, so I call this one like this. And then I have some other names for that. You have 10 seconds, yeah? Okay. Only that?
Yes.
Yes. CK, what are you taking?
Is there a land?
What is typical Swedish?
So maybe I should start with what I'm doing then. I'm probably taking, so then we have here 1, 2, 3, 4, 5, 6. And I will take the 12, I think. And my son will take, I think, number 3. So what is?
So I will take number 6 for the main course.
6. Yes.
That's called beef ribeye. Anything that requires.
So now I will do here A, B, C, D, E, and F. This is of course for 2 people, remember. Yes, what else? What are you taking for starter?
Yeah, I was wondering if I was going to take a starter because I'm not so convinced by the starter.
So then make it think about it. What are you taking?
I'm taking you trout.
Yes.
I think perhaps we can go for a direct course and have a dessert instead.
Trout, 20.
Huh?
Trout.
Yeah.
I will get number number 4.
No starter otherwise?
Number 4.
Huh?
Number 4. Yes, and then
Number 4 is
It's lamb. Yes. Okay then. All right.
So do we? So we forgot about the starter. Can we look at the dessert?
Yes, please. The dessert we don't need to order now.
No, no, but just to know if I'm
Yeah,
more. Yes, strawberry with ice cream.
Yeah, I think
Now,
so.
what would be nice to know is what they have the starter for two. Perhaps we could share that among all of us, you know.
Okay.
What is it exactly? This Inns herring plate
That might be
for at
actually
least
an
two
idea.
persons?
that's in the Swedish thing. It's a full fish barbecued or grilled. So it's grilled trout with anchovies.
Ah, okay. So it's trout again.
Forel. Forel.
Herring it says. It says herring. There's no trout. But it is, so I think it's more like a bit thicker
Sorry.
kind of stuff. I think it's, I mean, it's a typical Nordic, Danish. I even think it's more like a Danish thing. So I would think it's quite typical. And it's
What is it? Is it fish? Ah,
fish. Herring with fish.
okay, okay.
And,
I don't eat fish, I don't really know the name.
so at least then it's not a starter for you. But it is an idea, of course. So, but I don't know whether these starters ought to be up for sharing. I don't think we have had such a thing yet. We share starters.
Oh,
So we don't go for starters, yeah?
no.
All right. So then, thank you for the input. I will order that.
Thank you, Axel.
Sure. At least it's in walking distance, and it's. Do I need to tell you? Probably we walk all together, right?
We walk all together.
Yes. And
Let's
then
meet
so
at 7:15 or 7.
So it takes maximum 15 minutes, but it's maybe so it's 13 is the time that we start. So we could either leave at 4:15 or it was 10 past.
10 past, yeah, 10 past.
So we meet all at 19:10 in the at the entrance, I think.
Thank you.
Good. By the way, this has a magnet here.